Is there life out there, beyond our planet, elsewhere in the deep, dark universe? Many scientists think life on planets other than Earth does exist, and the search for other life signatures has gained momentum, making the aliens of science fiction more science and less fiction. But rather than wait for a potential future mission to a world of other living things, the Discovery Channel sent its own animated mission to a fictional planet 6.5 light-years from Earth, called Darwin 4. Using computer animation and motion geometry, artists filled Darwin 4 with alien-like features, ones that planetary scientists think could actually exist. Alien planet trees that dine on living things, and unsuspecting creatures that jump from branch to branch. Some are quick, while others walk very slowly across the planetary terrain. All of this animation, though very complex looking, can be broken down into simple geometric shapes and their transformations. One such transformation, a translation, is when one shape moves in a direction and travels a distance that can be measured. And though the shape's location changes, its size and orientation do not. Artists use translations to make these creatures walk across the screen. In a geometric rotation, a shape is moving or rotating about an axis along a circle. See how each point on the shape is moving in a circle around the same axis point? The shape and size don't change, but its orientation and location do. In a geometric dilation, the size of a shape gets larger or smaller, but the shape stays the same. Animators use this transformation to make it seem like things are moving toward or away from us. Why don't we move toward the alien planet and find a few more examples of geometric transformations while we're there? Let's go! The dagger wrist, the Unth, and the gyro sprinter. All of these unique fictional characters populate Alien Planet. Each has its own tricks. All three have been animated using geometric translations. The gyro sprinter is one of the fastest creatures on the planet. Whoa, let's slow him down. Look closely at its body. As the gyro sprinter moves across the screen, its location changes, but its size, shape, and orientation do not. See how each point moves the same distance in the same direction along parallel lines? Its direction is obvious, and we can also measure the distance it travels. These are all characteristics of a translation. We can slide or translate the shapes that make up the creature's body across screen. Notice how each point has moved along a parallel line in the same direction? This movement seems simple, but it helps animators bring complex imaginary worlds to life. Trees usually remind people of nice things: gentle breezes, cool shade, sometimes red apples. But the trees on Darwin 4 have butcher in their being. They're called butcher trees, and they have sharp daggers that dangle by their sides like dead branches that come alive when prey is near. If you look closely, you'll notice that each dagger is really a skinny triangular shape. It connects and rotates about an axis of rotation. Let's observe the rotation of its simple shape, a triangle all by itself. In a rotation, each point in the shape moves along a circle. This point on the triangle just so happens to be the axis of rotation, and all other points rotate around it. These 2 points rotate around the axis along a circle at the same rate, by the same angle in a given time. We can change this triangle and move 1 point farther away from its axis. The point will still rotate about the axis along a circle, but it will travel a longer distance on a larger circle than the points closer to the axis. No matter the shape, Anytime it is moving about an axis point along a circle, it is rotating. Trees aren't the only creatures that eat their prey on Alien Planet. Creatures eat other creatures too. The arrow tongue resembles the T-Rex and has similar hunting sensibilities. While on the hunt, animators make it look like we're zooming in on his prey, signaling that he spotted something, perhaps some dinner. To create this effect, artists use dilations, making the shape, in this case the prey's body, grow larger, all the while maintaining its shape. For example, look at the arrow tongue's eye. In a dilation, each point in the shape moves along an imaginary line that extends from the center of the dilation, the middle of the arrow tongue's eye, for instance. When dilating, the shape's size changes, but its form remains the same. That's because each point on it changes its distance from the center of dilation by the same ratio. Suppose the radius of a circle, the distance from the center to any point on the circle, is 2 inches. If the circle dilates, the radius of the new larger circle will be larger and will have grown by the same ratio compared with the previous size. That means that each point on it must increase its distance from the center of dilation by the same proportion, doubling. That growth, compared to its original distance, is called a scaling factor. Its new radius of 4 inches is twice as much as the original circle's 2, so the scaling factor is 2. What would happen if some points changed their distances from the center of dilation by different ratios? The shape would be distorted, of course, and we'd no longer have a true dilation of the same shape. Animators don't want a shape to be disfigured when changing its distance, such as when zooming in. That wouldn't be realistic. They just want the distance to appear to change, using dilations to make that happen. And that's an arrow tongue on the hunt.